So we ended our last lecture with the derivation of this expression for Taylor series fx equal to fa f dash a into x minus a plus f double dash a divided by 2 factorial into x minus a square plus dash 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 plus fn minus 1 divided by n minus 1 factorial a x minus a n minus 1 plus integral a to x n times fn x dx raised to n. So this integral, multiple integral, it is called a remainder. We call it remainder of in the Taylor series and write it as n or nx or nx. Therefore, or nx or the remainder in Taylor series is or nx is equal to integral a to x n times, of course, a to x will just make 1, then put 3 dots and then ax. This means from 1 to n, then fnx dx n times dx raised to n. If we now use this or nx for this Taylor series, we can write now fx as fx is equal to fa fx is equal to fa plus f dash a x minus a then dash dash dot dot then plus f n minus 1 a. All derivatives are to be evaluated at point a divided by n minus 1 factorial then x minus a raised to n minus 1 plus or nx. This then is another form of this Taylor series. Now before talking about the value of Rnx, we must be able to integrate this expression. Say suppose we will take it up from this simple example. Suppose you have integral a to x dx, just 1 dx, a to x dx. That will be simply x minus a, simply because integral dx will be x, and when you take these two these limits, x minus a. So if we have now, instead of this, if we have two such integrals, it is a double integral dx square. So what will we do? We'll do this thing. We will take ax and then ax dx, and then next what we do is we take ax dx. Now you have now this is just this. Now you have already evaluated this. We write ax. This has been evaluated already. This is x minus a. Now x minus a. This is x minus a into this dx. The limits are same now, but when you integrate now this, it will become x minus a divide x minus a square divided by 2 divided by 2. After, of course, after these using limits, you will still get the same, because upper limit is x, lower limit is a. No, there is no difference. There will be no difference. So it is x minus a square divided by 2. When you integrated once, you got x minus a raised to 1 divided by 1. Now when you integrate twice, you got x minus a square divided by 2. Similarly, if you integrate it 3 times, you will get x minus a whole cube divided by 3 factorial. It will be factorial. You can see it. Let us check it. Now we have ax, 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 dx, dx, dx. Okay, but now we have already evaluated these two, and we have got it. We saw it is x minus a whole square divided by 2. Then we are now left with this ax. This much is the value of these two together into dx. Now take this 2 out, 1 by 2. Now integrate this x minus a whole cube divided by 3. You can see the factorial. That is all about this. Now we have x minus a whole cube divided by 3 factorial. Now it is now quite easy for you to see what this will be equal to. A x, then again ax n times, and dx n. Naturally this will be equal to, since you are integrating n times, you will get x minus a raised to n divided by n factorial. Okay, we will be using this result now. Where we are going to use this result, see, we have seen that reminder or an x is equal to integral ax, then again integral ax, then fnx into dx raised 5. Now in this, sorry, not raised 5, raised n. Now in this particular case, fnx is not a constant and hence cannot be taken out. Hence, in order to evaluate this, we must know fnx, but that's not needed. That we don't need. Just let us mark this as equation 1. See, fnx is the nth derivative of fx. We assume that this fnx is continuous over this interval ax. You know, our Taylor series is being expanded about this a in this interval a to x. I will explain this, what it means expanding over about a. Now fnx, that means nth derivative of fx. We assume that it is continuous in this interval. By continuous means that it takes all possible values between a minimum and a maximum in that interval. Suppose we have, let me give as an example a few values that fnx has in this interval. It's just an example. Suppose it has a value, say 5, then 3, then 1, then 9, then 11, for example. Out of these values, one of the value is the least value, this least value. We denote it by small m. There is another value which is the maximum value, the highest value, that is capital M. Let us denote it. We can easily write then fnx is greater than or equal to m. It is minimum value. Less than or equal to m. It is maximum value in this interval. Okay. Right. Now, if we now do one thing, let's go first to this. So I have seen, we have seen how fnx is greater than m, less than or equal to m. Small m is its least value in this interval ax, and m is its highest value in the interval. Okay, now let me now do one thing, that is, let me integrate all of them n times. That means let me integrate, for example, this a raised a to x n times. I'm going to integrate all of them n times m dx n less than or equal to this to integral ax fnx dx n dx n. Then this less than or equal to integral ax ax fn no m m m dx raised to n. Let's carry out the integration. Now see, we can now easily carry out its integration. M is constant, it will come out. When m goes out, then you are left with a raised to x dx raised to n times. And you know, we have just calculated it. M is out, then m, this much will be x minus a raised to n divided by n factorial, as we have seen in on one of the last pages. Then there is this is what we defined as the remainder. This is the remainder, or nx, and this is again m, just this m x minus a raised to n divided by n factorial. Okay. Now you have now suppose we can do one thing. We can now do this thing, that we transfer this or let us multiply all of them by this reciprocal of this. That means n factorial. I will multiply all of them by this n factorial divided by x minus a raised to n. When I multiply this by this, n factorial will cancel. X minus a raised to n, x minus 3 raised to n will cancel. I will be left with m here, m. Now multiplying this with this will give me n factorial divided by x minus a raised to n factorial n raised to n into or nx. That will give me here this n factorial, they will cancel. X minus a, x minus, I will be having m. So what do I find? I find this quantity lies between m and m. Okay, now of course, as this expression shows you that the value of this will depend upon x. It will vary with x. We will discuss that a bit ahead. Now we have reached this conclusion, and we have reached this conclusion. Now see, look here. Now suppose let this be at a particular point. There is a point in this interval. There is a point, say c somewhere between the two, not necessarily exactly midway between the two, but inside the interval, this interval. Now at that point, this will have some value. This will have this expression will have some value. What that value will be, I can yes, that value will be, say let it be k. Let us say that value is k. So let me go to this. That value is k at that instant, at that point. Now, whose value is k? I mean, this value is k. Why does this k lie? It lies between m and m. So back to this m and m. Okay, but we also know that f and x also lies between m and m. Back to this f and x, because this is its minimum value, this is its maximum value. Now is the interesting thing, that is, there is an interval a and x. Now f and x is continuous and it starts from value m and ends at value m in this interval. That means it go now. If something is continuous, f and x is continuous. Okay, it is continuous. It starts from some value. It is minimum value. Say 2 minimum values, for example 2, and it is not necessary that minimum value will occur at this point. It will occur at some point, but it is I'm not talking about value of x. I'm not talking about this value. Suppose I plot a graph. Here I plot x. Here I plot fx. I'm not talking about value of x. I'm talking about value of fx. Fnx has minimum value 2, maximum value say 11, maximum value 11. In between, whatever values there are in between these two, those values, this fnx will definitely pass through those values because it's continuous. It is continuous. Continuous means that it cannot have a missing value. That would mean a discontinuity, a gap, a discontinuity. So because of this, all the values that lie between these two values must be values of f and x. Of course, not at one point, at different points, corresponding to different values of x. It will have all those values that range between 2 and 11. Since k is one of those values, k lies between these two. This means that somewhere f and x will have this value. Somewhere, where, let us say at a point that we denote by c. Somewhere, that means f and c will be equal to k, because k is a point, is a value that lies between these two. K is a value that lies between these two, and f and x takes all the values that lie between these two. Hence, f and x has to somewhere equal this k. It has to become k somewhere, and let that somewhere be c, that lies between a and c. Therefore, we can say that reminder. Let's go back, because k was this. This was k. So we can say n factorial divided by x minus a raised to n or n x, which is k, of course. N factorial, I mean this, or first let me write fnc is equal to k n factorial divided by x minus a raised to n into or n x back to this n factorial divided by x minus a raised to n or n x. Okay, coming back to this, we can now find out value of r n x. R n x is equal to fn c into x minus a, because this will go there, x minus a raised to this, and then we have divided by n factorial. Let me write that here, n factorial. Therefore, this is the value of our remainder. Therefore, Taylor's theorem can again be written as fx is equal to f a plus f dash a plus dash 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 plus. After writing some terms, say I write n minus 1 terms, last term that I write here is n minus 1 into n minus 1 at a divided by n minus 1 factorial into x minus a raised to n minus 1 plus whatever is left after this term, that is clubbed under this. We can write that fn c x minus a n divided by n factorial. Let me clarify this first. In Taylor series, there are infinite terms. Now, When you write these terms 1, 2 and n minus 1 terms, you could have written nth term as well, or n plus 1th term, n plus 2 term, n plus 3rd term, n plus any, but whatever is left after that, the last term that you write, here I have written the last term this. And this series does not end here. If I don't write this in this expression, I will be having an approximation, not an exact value of fx, only an approximate value. Whatever is left, somewhere I have to end. So whatever is left after writing out, say some terms explicitly, whatever next is left is taken as reminder. We call that reminder, and that reminder can be that reminder is equal to this, is equal to this value that we proved. Now, good. Now one more thing, that is, having said this, now we go to, say, for example, suppose one, yes, you should be clear about this. That is, you need not finish it here. You can write it. You can write one more term like this. For example, you can say, for example, you can write fx, and this is, there is not 100% agreement regarding the same. Some people write n last term as n minus 1 term. Some write n nth term. So if you write nth term as the last term, then you will get fa plus f dash a plus f double dash a divided by 2 factorial plus dash 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 plus dash 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 plus. Now I can write this fn x divided by n factorial. X, sorry, I have not written x minus a square, x minus a raised to 1, and x minus a raised to n plus whatever now is left, it will be called this reminder, and that reminder now will be, that will be f n plus 1, not n plus 1 denoted by n plus 1, c divided by n factorial x minus 1a raised to n. You can write Taylor's theorem like this as well. Now you have this. You can see it. F and C, instead of, I did not end the, I did not take this last term. I took one more term after this and treated that as the last term. Whatever is now left is not to be denoted by f and c. Now it is fn plus 1 c x minus a raised to n divided by n factorial. Now after that, let us go back to this. See, we have now that is okay, but see, what about this? Just a minute. Regarding x minus a raised to n, x minus a raised to n is here, so it should be x minus a raised to n plus 1, and then there n plus 1. Yes, n plus 1 factorial. Okay. If we do one thing now, we take n equal to 0, put n equal to 0. What does that mean? It means that I will restrict Taylor's theorem to the first term, that I will take this term. I will not take that. N equal to n, you know what n denotes. N denotes the order of the derivative. N equal to 1 means first derivative. N equal to 2 means this derivative. N equal to 3 means this derivative. But when you put n equal to 0, that means you are not going to take these derivatives. You have then add, in that special case, you have fx is equal to fa. Okay, none of these derivatives is to be taken. Okay, then you are left with this. Then this f, you have f, when you put n equal to 0 here, n equal to 0 means f1 divided by n plus 1, that is 1 factorial, that of course is 1, x minus a raised to this n plus 1, that is 0 plus 1, that is 1. Now f1 means first derivative evaluated at c. Evaluated at c. So if we now write it again here, we can again write it here in this form. We have fx then equal to fx equal to, after this I am going to this, fx is equal to fa plus this is f dash c, first order derivative, x minus a. Okay, now I transpose this to this side, I get fx minus fa is equal to f dash c x minus a. In my next this step, what I will do, I will transpose this x minus a to this side. When I do that, I get fx minus fa divided by x minus a is equal to f dash c. Now go back and see whether fx minus fa divided by x minus a is equal to f dash c. Good, f dash c. But the same can be written as f dash c is equal to fx minus fa divided by x minus a. But what is this? What this is? Yes, let us see what this is. You suppose you have this fx. This is fx. Suppose it is fx. A here, this is fa, and here fx. When you take fx minus fa, you are actually taking change in the function. This is change in the function divided by corresponding change in x. This is x, this is a, x minus a, change in x. So change in the function divided by change in x is rate of change of function, but this rate of change is its average rate of change, because you are taking final value minus initial value and divided by x minus a. Then the resulting change is not actual rate of change, it is average rate of change. And this theorem tells us that this average rate of change, there is a point between these two, where this average rate of change will be equal to actual rate of change, f dash c. After all, what is f dash c? Dfc by dx. That means dfx by dx evaluated at c. So suppose this is the point. At this point c, the actual rate of change, this average rate of change and actual rate of change at this point will be same. This is called mean value theorem. A simple example will make it clear. Suppose a body accelerates from 0 to 20 meter per second. 20 meter per second without any stop. It continuously accelerated from this to this. This means that it will be taking all the possible values that lie between 0 and 20, and it took, now it since it accelerated, or let me say like this, suppose it covered a distance of 20 meter, and it took distance covered was 20 meter, and time taken was 5 seconds, for example. Then what is the speed of this vehicle? Speed of the vehicle is 20 meter divided by 5 seconds, that is 4 meter per second. But that is only average, because the vehicle did not move with the same speed from this point to this point. It accelerated. Its speed was 0, then it attained some speed, then some other speed, somewhere it was moving with 2 meter per second, somewhere it was moving with 6 meter per second. The average value of its speeds was 4 meter per second, average value. Now mean value theorem tells us that there is a point between these two ends where the actual speed of the car will be exactly 4 meter per second. So when the car is accelerated, suppose at the beginning its speed is 0, then 0.1, then 0.2, then and so on. As it changes continuously, there is a point 4. There is a value 4 that also lies between 0 and 20. This 4 lies between 0 and the car will certainly have this speed at some instant of time. That means actual speed at that instant. Suppose this speed is here. So at that time, when the car is passing through this point, its actual speed is the same as its average speed. This is a property of continuous functions. I hope this is clear to you. Mean value theorem is very important and very useful. So please remember this thing. This C, of course, is a point between this and this. Between this and this. Now let us go to another topic. Now we have now had this, and we have actually derived this Taylor's theorem. Then we saw mean value theorem. Then now next we have a very important thing that will be used, of course, that will be very useful for us in dealing with complex functions. Now that is, if we have a function of more than one variable, more than one variable, then one variable, more than one variable, then suppose till now we had a function fx, something depending upon x, only one variable. We next have function depending upon two variables, x, y. As an example, to show you, to give you some idea, suppose house price of houses in a colony, price of a house in a colony, price P, may depend upon several factors, several these variables. For example, it may depend upon plinth area, A means area, it is plinth area, or it is location, L location, or number of bathrooms. If it depends upon two variables, then it is a function of two variables. If it depends on more than two variables, it's a function of multivariables. So you can think of, say for example, gravitational force between two masses that depends upon not only masses but also distance between the masses. So it is, gravitational force is a function of two variables, more than one variable. Now suppose you have when you go to more than one variable, initially you had only one variable, that was x, and we used it to show it along this horizontal line, the real number line, and that was all. That is all. We had a value a and another value x, and then we called this interval from a to x. Now the situation will change. You have x variable here, y variable here, x variable here, y variable here. It is not fx here, fx not here. Now this is not fx, no more fx along this. This is variable, just like x variable. Where is fx now? fxy, not fx, fxy is up, somewhere here, up or below this plane. This means that now x and y, the input variables, or lie in a plane rather than on a straight line. They lie in a plane. Now when they lie in a plane, the interval suddenly changes. Instead of one dimensional interval, we will now have a two dimensional interval, something like this. That means our x and y can have this pair. We have a pair xy, so we will have, for every point we will have two values, two coordinates, x and y. Suppose we have a point here, it will have some x, that is x, and this is its y. Similarly, we have point here, this is x, this is y. Similarly, other points, all points on this line used to have only one this this coordinate. All points on that fx line, that x line. So all points on that line had just one coordinate, that is x coordinate. But now points on this line will have more than one coordinate. It will have x coordinate, it will have y coordinate. So each point now will be having two coordinates, and instead of line we will have an area. This area is normally called a region, denoted by R. Not to be confused with range. Region denoted by R. Now suppose I now have a particular region. Say this is X, this is Y, and this is the region that I have, this particular region. And in this region I have two points, two fixed points. A, B is 1 point. There in fx case we had only A for the first point, but here we need 2 points, two coordinates for each point. So the first point will have two coordinates, followed by second point. Second fixed point is here, and its coordinates are x naught, y naught. These are 2 points. We can, since there are only 2 points that we are considering right now, we can join them by a straight line. This is the straight line. We can now, you know that we can, since we don't have fx, we have fxy, a function of two coordinates. Now we can have now see this line. Yes, of course, we have two coordinates, and since we have been dealing with one coordinate function, those that experiences with us, so we would like to convert this case of two variable case into a single variable case. That is possible. We can convert it into a single variable case. That is possible. How that is possible? We use another variable, a third variable. Instead of x, y, we use a third variable, say t. We call it t. This t single-handedly does what x and y together do. What does that mean? That means x and y identify these points on this line. Each point on this line is identified by x and y. Now I will define t in such a way that t single-handedly will do the same thing. How? Let me take this variable t as the length of this segment, line segment length, but in such a way that the total length of this segment is 1. This is called normalization. I am normalizing it. That means if it starts here with 0 length, here its length is 0, and as you go on, its length goes on increasing. The maximum length that it achieves at this other fixed point that I define as 1. Other points on this segment will have a value of t that will be fraction. That will be a fraction. So t, I am defining t a variable in such a way that it is greater than or equal to 0, less than or equal to 1. In fact, this variable is called a parameter. We call it parameter. Now I can express now this coordinates of any point. Say suppose we have a point here whose coordinates are xy, or the transition coordinates, that means coordinates that change xy. So I can express coordinates of this point in terms of t easily. Here is the expression. I can write x is equal to a plus x naught minus a into t. Then y is equal to a b plus y naught minus b into t. We can check it out. If we put t equal to 0, suppose put t equal to 0. See what will x and y be. When you put t equal to 0, this whole portion will be washed out, and this whole portion will be washed out. You will get x is equal to a, x is equal to a, y is equal to b. So x is equal to a, y is equal to b when t equal to 0. So this means that that is what actually we defined. That is how we define t. This means that t equal to 0 represents this point, a, b point, x equal to a, equal to b. Now t equal to 1, put t equal to 1. See what x will come out to be. X will be equal to a plus x naught minus a. Because t is 1, so a will go, x is equal to xo. Similarly, y is equal to yo. Good. Now, what is the advantage? Why do we do it? Why do we introduce this? Yeah, the reason is that it will transform this fxy into a single equation, into a function of single variable. How? Let us see. Let me write fxy. fxy is equal to f x is equal to a plus x naught minus a into t into comma y naught. Now, y is b plus y naught minus b into t. Okay, now do it. Let's do one thing. That is, let's have a look at it. A is constant, x naught is constant, fixed point x naught. X is not constant, but x naught is. A is constant, t is the only variable here. From this to this, we have discovered one variable, that is t. From this to this, b is constant, y naught is constant, b is constant, t. That means from this to this, there is only one variable. What that variable is? That is t. This means this function is function of one variable, that is t. We can write this function as ft. Now, if that is the case, then we have actually converted fxy into ft, a single variable function. Assuming that this ft is continuous and infinitely differentiable, then we can write a Taylor series for it. And the Taylor series is for ft. Taylor series is ft is equal to f at the initial point. What is initial point here? Initial point is this point. And at that point, what is the value of t? Value of t is 0. Initial point, that is 0. Value of t is 0 plus f dash evaluated at initial point, that is 0, divided by nothing, into x minus a. See, it is x minus a. Now here you have a. Instead of a, you have t, and t equals 0 at a. That means at this point t equal to 0. Correct? T is equal to 0 here. So we have this as we are left with t minus 0. This t here means coordinate of this, called t minus a. I have to write t minus a, but for a, t is 0, so I write it t minus 0. That is simply t. Then we have f double dash 0 divided by 2 factorial t squared plus dash dash plus we have now then f n 0 divided by n factorial t raised to n, then rest is the remainder, and remainder is f n plus 1 into c evaluated at some middle point c. Now this middle point c we will discuss it just now. We will discuss it divided by fn plus 1 c divided by n plus 1 factorial into n plus t raised to n plus 1. Now see, in the previous single variable case, we had x, and c was a point between them. C had one coordinate, that is c, but now c will be a point between a and b. That means c will be a point here, somewhere here. C will be somewhere here, and this c will have two coordinates. Let's denote those coordinates by we will have this coordinate. What should we write them? What should we write for them? Say we write them alpha beta. Let's write alpha and beta for them. So I can write here alpha and beta instead of this. Okay, alpha and beta, keep that there. alpha and beta, alpha, beta, okay, or here alpha, beta, coordinates of that midpoint. Not midpoint, that is somewhere where this reminder is evaluated. Now, in order to find these, we now need this. Say we need suppose we have to find, first let us take f naught. F naught means t equal to 0. You have to put t equal to 0. That means if that is t is equal to 0, this means this f a b, t equal to 0. Yes, f a b. Very nice. Now that is let us keep it as it is. F0 is F0. Okay. Next we have f dash t, f dash. If we want to evaluate this f dash, we have a problem. We have to find out a derivative of this ft. We will need first to evaluate f dash t. Then in that f dash t, we will have to put t t equal to t equal to 0. Sorry, this is 0. T equal to 0. Okay. First of all, we have to find f dash t. But finding f dash t means d by dt ft. Okay, d by dt ft. Let's denote this d by dt by capital D operator, differential operator. So ft, dft. Now to find this d, I have d is equal to d by dt, which can be written as d by dt can be written as d by dx by dt plus del by del y into del dy by dt. Now the question is how, why I am doing this, why I am writing this. Now imagine you are going to differentiate a function with respect to this, with respect to t, a function ft. But ft basically is fxy. So I can, instead of f, I can write here fxy. Now when you differentiate fxy, a function of two variables x and y, with respect to t is not explicitly there. It is not explicitly there. So what we do, we differentiate this fxy with respect to x and y. We differentiate it with respect to x and y. But then we use chain rule to find out its derivative with respect to t. That is how that is what I am doing here. So I am writing it is you should read this as d by dt fxy. So it is here df with respect to, here you are differentiating this with respect to x, keeping y constant. That is why there is partial derivative. Now here you again f, and here you are differentiating it with respect to y, keeping the other variable constant, that is x constant. This is why we define this d as this operator as see d is equal to d by dt and then d by dt is equal to, then we had this d by dt is equal to d by del x dx by dt plus del by del y dy by dt. Now this dx by dt and del dy by dt can be easily found from this no, here, sorry, just a minute. Yes, we have it here. This is x is equal to this. From this you find dx by dt. Let's first find dx by dt from this. dx by dt is equal to a constant, this constant, dx by dt is equal to simply 1. No, it is dx by dt. we're finding it dx by dt, that is a is constant, x naught minus a, that is this is constant, a is constant, we have t, that's 1, dx by dt is 1, and then we have again next we have this dy by dt, dy by dt is again 1. Is it okay? Are we going rightly, proceeding ahead rightly or not? So we will have this x df by dt, df by dt, it is x dx by dt, that is okay, it is okay, it seems okay, quite okay. Sorry, I'm wrong. This is this is why sometimes we make wild mistakes. A vanishes because now here t vanishes, but x naught minus a remains. X naught minus a remains. Sorry, y naught minus a remains. Y naught minus b. Sorry, b remains. After having found these two, x naught minus a, y naught minus b, we go back. We go back here. We have d is equal to dx by dt, that is x naught minus a into del by del x plus del y by del, that is y naught minus b into del by del y. Okay, this is d. Similarly, we can then find, say, so we have now, till now we have f dash, now we have to evaluate f dash this 0, f dash 0. So f dash 0 we write is equal to f dash t and t equal to 0. That means you have to evaluate at t equal to 0, which means you have to write it, f dash t is d by dt, okay, d by dt ft, to be evaluated at t equal to 0, but that is equal to, I can write d for this, d ft. ft is, instead of ft, we can write this f xy, okay, f xy, but at, to be evaluated at a b, because initial point which corresponds to t equal to 0 in Cartesian coordinates is corresponds to AB. So this is our first derivative, f dash 0. Similarly, we calculate f double dash 0. That again will be like this. We can write it this d by dt of f dash 0, d by dt of f dash 0, because it is, then I can write d by dt f dash 0. Instead of f dash 0, I can write d by dt f 0, or which is the same as d square. This is d square f. Convert this to back to Cartesian coordinates. So it is f xy. This whole is to be evaluated at this AB. With these three, this enough. I think this is enough. Then we can now write, we have already fxy, as you know, fxy is equal to ft. Now at t equal to 0, now we have to write this for, say, suppose this, I will take, this was the region, and this was the line that we considered. It had AB here, it had x naught y naught here, just like that. In a single that case, we had a here, x here. Here instead of xy, we have x naught y naught. We write x naught y naught. Okay, x naught y naught is equal to ft. We can also write fx, that this x naught y naught, or fxy. Let's keep that fxy, because we will be using this transition coordinate fxy. fxy is equal to ft, then this will be this will be now, first of all, first term will be fo. Now since fo, so we have here this fo is simply fab, that is ab, or if we take 0, ft equal to 0, that is this point, or we can take this point fxy xo yu. We can, if we take xo yu, then it will be which of those, which we are expanding this about this. Then if that is the case, then we have to write x naught y naught here, and then value of this